Welcome back, kids and coaches. Welcome back to Algebra 1. Today we're doing 716, the last new lesson that we were doing before our Chapter 7 test next week, Monday. So, a couple announcements again. Make sure we have all of our homework turned in. This upcoming homework collection, homework 13, we're going to have an extra credit assignment included on that. So stay tuned for live class later this week. We'll talk more about that. And then tomorrow we do have Formative Quiz number 11. So if you're watching this, make sure you check It's Learning tomorrow to take that quiz. Other than that, that's pretty much all we got for announcements. Test next Monday. Start studying for that. Best way to study is doing your homework, asking questions in class, and coming with homework questions for us to answer in class is probably the best way that you can study. So first thing we're going to do, I'm going to put up the answers very quickly for the homework, and then we're going to jump right into 716. So again, if you want to check these answers out in a little more detail, pause that video and moving on. All right, so we're going to start with a little warm-up problem today. So Brianna has a savings account that started with $1,000. She always adds $50 to it every single month. What equation models her account growth the best? So first of all, let's try to figure out, is this going to be linear or is this going to be exponential? So if we're thinking about she adds $50 every single month, she adds the same amount every single month. To me, that doesn't seem like it's going to be an exponential function because, again, if she's adding the exact same amount over and over again, that growth is going to be constant because she's adding the same amount month after month after month. So I think we need a linear equation for this one, again, because we are growing by a constant amount all the way through every single month from here on out. So I think B is going to be the best bet for us right here, where, again, our starting value, that y-intercept, if we were to graph this, would be $1,000. That growth or slope value is 50 times x, where x is the number of months. So I think B is going to be the best equation for us instead of D, which I don't know if we can see or not. Right here, we'll be flipped the other way around. So if we pick D, this would tell us that we're growing by $1,000 a month and starting with 50, which is not the case. So awesome. Well, let's jump into 716. So what I want everybody to do today is kind of it's tying everything together that we've talked about with exponential functions so far. It's being able to take a situation or take a graph, take a table, take an equation, and basically write a situation that might represent that, or write a problem that might represent that, like in 767. Taking our graph, or just taking a word problem, being able to write a graph that kind of fits that situation, writing an equation from from a problem, and then being able to use that equation to solve different problems. So it's kind of tying everything together that we've talked about so far in Chapter 7. So what I would like everybody to do at home is first pause the video right here and then work through this lesson on your own before you watch the rest of the video. And then if you get stuck working on any of the problems as we go through, or as you go through the lesson, then come back to the video and check your work there. Because again, this is kind of like, again, tying everything all together, so hopefully we feel pretty comfortable with exponential functions by now. So try to work through this one on our own first, and then if you get stuck, come back and watch that corresponding section of the video. We're going to start with 768. If you're stuck on 767, that's going to be at the end of the video, so just kind of come back to that one and come back in just a little bit. So first one, 768, a virus has invaded Letitia's favorite mountain fishing lake. Currently there are an estimated 1,800 trout in the lake, and the Fish and Game Department has determined that the rate of fish deaths will be 1/3 of the population per week if it's left untreated. So the first thing we want to do is make a graph. So here's how I made my graph. I put the number of fish on the y-axis. If I can get my picture out of the way on the bottom. I've got the number of weeks on the bottom here, which, let's see, let's add a little bit. There we go. So number of weeks on the bottom, number of fish on the left-hand side of the y-axis, weeks on the x-axis. So again, we know we start with 1,800 trout. So I'm going to put that dot right here. That's our starting point. And then we know that we're going down by 1/3 of the population every single week if we're left untreated. So we know our graph, if I just kind of sketch very roughly, is going to look something like this for an exponential decay function or decreasing function. So if we kind of just plot the next couple of points really quickly, we get something that starts looking along the lines of like this, which it would match that shape exactly. Oops, let's maybe try that line one more time. And we're not trying to be super precise. This one is just trying to say sketch the overall shape of what that graph would look like, which would be something along the lines of that. So this next one, in theory, think back to our Penny Lab. We had a very similar question like this in that class day. Theoretically, will the trout ever completely disappear from the lake? So again, when we have an exponential decay function or exponential growth, we always have an asymptote at y equals 0. So what that means again is that we get closer and closer and closer and closer to 0, but we never actually get there. So theoretically, since again we have an exponential decay function on our graph up here, theoretically we will never get to 0. So again, because y equals 0 is an asymptote for our exponential function. Perfect. That's all we got to do for that one. Pretty straightforward. Let's go to the next one, 769. We're going to talk about some fees for attending public university. So let's see here. In 2010, it cost $7,000 to go to college, and the annual cost increase is shown in the graph at the right. So note that X is the number of years and Y is the amount of money it costs. So let's see here. This is just like we did yesterday. So first thing we want to do is write an equation to describe this situation. So we need a couple of things, knowing that our exponential equations are y equals a times b to the x. We need our starting value, which is our y-intercept on our graph, and then we need our multiplier, which we'll find in just a second. So again, we know our y-intercept is 7,000 because at x equals 0, we know that corresponding y value of 7,000. So we have our equation so far as y equals 7,000 times something to the x. We just got to find the something. So yesterday, again, we reviewed how to find a multiplier. So b we can find by taking any term or any y term and then dividing it by that previous y term. Oops, come on. Let's get it back to the marker. Any previous y term. So if we apply that to our graph, we have x is equal to 1, x is equal to 0. Those corresponding y values are 7,700 and 7,000. So we have any y term. We know the previous one from 1, which is x at x equals 0. So for this, we have to say 7,700 divided by 7,000. And when we evaluate that, we get our multiplier of 1.1. So now we can plug that into our equation, and we get 7,000 times 1.1 to the x. All right, so next we want to figure out the cost of attending college in the first year that you would be eligible to enroll. And I know most students in Algebra 1 this year are graduating, I believe it's in 2021, so that would, or not 2021, 2024, which would mean that would be the first year you'd be eligible to enroll in college. So that's what I'm going to use for x. Again, knowing that our x-axis over here, if I get rid of the thing, or that little circle, the x-axis tells us the number of years after 2011. After 2011. So we need to use x is equal to 14 to figure that out. So, which would be the cost of college in 2024 for the freshmen that are in the group. If you're a sophomore taking Algebra 1, you could plug in 13 and find the same thing here. But here, that would make our equation y equals 7,000 times 1.1 raised to the 14th power. When we evaluate this, remember we have to do this term first before we do anything else. So exponents first, then we can multiply that by 7,000. And when we do that, we end up getting $26,582 if we just round to the nearest whole dollar. So the cost for 1 year of college at a public school in 14 years after the year 2010, which is only 3 years from now, it would be $26,582. So what is the cost in 2012 or 2000 in the year 2000? Well, I don't think any of you were actually even born then, but what is the cost in the year 2000, assuming the rate of increase is the same during the time period from 2000 to 2010? So again, knowing that at x is equal to 0, so this line right here, this is the year 2010, we got to go back this way 10 years to figure out that what that cost of college is at in the year 2000. So our x value here is going to be x equals -10 to tell us the cost of year 2000. So again, if we plug that into our equation, now that would get us y equals 7,000 times 1.1 to the -10, which if we evaluate would tell us that we would get a cost of college that is $2,000 or $2,698.50 for the year, which that is a bargain. Almost makes me wish we could go back in time and go there. All right, so how confident are you in your prediction from Part C? Honestly, I wouldn't be overly confident in that number, just because I doubt the cost of college increase stayed the same for the last, well, let's see here, for 10 years in a row that rate stayed the same. So we're making a pretty big assumption there for Part D. So I would doubt that it stayed the same, but there's a chance that it could have. All right, so next one and last one for 69. So if the actual cost for 2012 was $8,244, how accurate was the model? Well, let's plug in x equals 2 and figure it out. So if we want to check how accurate the model is, let's find what the model tells us for the cost for the year 2012 and then compare the two. So that means we got to plug in x equals 2 to our model. So y equals 7,000 times 1.1 to the second power, which if we evaluate that correctly, we get $8,470 even. So if the cost was actually $8,244, how accurate was our model? Well, let's take a look. So this is our projection, $8,470. If we subtract what the actual cost was, no, that's not what I want. Come on. 8,470. We're subtracting the actual cost, which was $8,244. That's a difference between those two of $226. So that means, because the cost or the actual cost was less than what our model was telling us, is that the cost of college isn't increasing as fast as our model initially told us, which is good news because college is already expensive enough the way it is. Perfect. Let's move on to the next one, or 770. So this one, we just want to make a reasonable sketch of each of these graphs without making a table first. So first and foremost, there's a little typo here in the graph, or in our notes. Y equals 1/2 to the x. This should actually be y equals 10 times 1/2 to the x. So that'll make a little bit of a difference. But other than that, we should be able to make a pretty decent guess of what these things are going to look like just by plotting a few points. So keep in mind, when we have, again, our general form, y equals a times b to the x, a is our starting value or our y-intercept, b is that multiplier. We know that if b is greater than 0, or not greater than 0, sorry, greater than 1, if b is greater than 1, we have an increasing function. And if b is between 0 and 1, then we have a decreasing function. So if we can figure out those two things just by looking at our graph, we should be able to have a pretty decent estimate if we're going up or if we're going down for our exponential graphs here. So let's start with A. First one, that first value is 5. That tells us that our y-intercept is going to be 5. So let's count up 5. 1, 2, 3, 4, 5. Perfect. 3, is 3 bigger than 1? Absolutely. 3 is our B value. So we know that our graph is going to start small to the left. It's going to go through that point and get really big as we go to the right. Just as a really rough guess. If you want to be more accurate with your graph, what you can do again is just make a table and then compare the two if you want to get more accurate than that. But we're just making a reasonable sketch for what this looks like. All right, number 2, or part B. What does it look like if we have 10 times 1/2 to the x? So again, that first value, 10, is our y-intercept. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1/2 is not bigger than 1, and it's between 0 and 1, so we know we have a decreasing function for our exponential function here. So that means we're going to be starting really big on the left, and we're going to get smaller as we go to the right and getting closer and closer to 0. So our graph would roughly look like this. And then lastly for C, here they're trying to be a little tricky with us, but this fraction is our A value. So we're just starting at 1/10, which is barely above the y, or the origin there. And then our multiplier is 5. Again, that is obviously bigger than 1, so we have an increasing function again. So we're going to start really, really, really small as we come from the left, and then get bigger and bigger as we go to the right. And that's how that one would look. All right, perfect. Let's go to 71. We'll keep cranking away here. Now we just want to write an equation for each one of these and answer the respective questions. So these are pretty straightforward. So write an equation, and then figure out what these are asking us and just plot those points, or just plug in the numbers and solve for those various things. All right, so a 100-gram sample of radioactive isotope decays at a rate of 6% every week. So how big will the sample be 1 year from today? All right, so we know a couple things. First, we're starting with a 100-gram sample. So that is our A value for our exponential function. So that is what we're going to start with. We have decay. So we know we're going to be decreasing. Isotope decays at a rate of 6% every week. 6% every week. So now we got to think. If we're starting with our 100% of our sample, so that 1.00, 100%, we're taking away 6% every week. So we're subtracting 6% from that 100% or 1.00. What we're left with is 0.94. Because again, we have to turn that percentage into a decimal and subtract it away from that 100%. And that is going to be our multiplier. So 0.94 will be our multiplier here. And another very important note is that x represents the number of weeks in this case. So our equation, y equals 100 times 0.94 to the x. And if we want to figure out the sample size, or how big the sample is going to be from a year from now, we need to know how many weeks are in a year. So 1 year from now is 52 weeks. So that means we got to plug in x, or 52 for x, and then we can solve. So y equals 100 times 0.94 to the 52nd power, and we will get 4.005 grams. Wonderful. Let's keep moving. Part B. Now we're talking about the Math Club. The Math Club is the most popular club on campus because of the Pi Day festivities on March 14th every single year. Each year the club's enrollment increases by 30%. So again, we're kind of starting with this same kind of idea here, but now we're going the other way. We'll talk about that in just a second. If the club has 45 members this year, how many members will it have in 5 years from now? So again, starting with 45 members, that's our A value. Our enrollment is increasing by 30% every single year. So for our multiplier, again, we're starting with that 100%, 1.00. That's the current membership. We are, in this case, we are adding 30%. And how we represent 30% as a decimal is 0.30. So we have to add 0.30 to our overall 100% of the members. So our multiplier is going to be 1.30. So now let's write an equation. Y is equal to our A value, it's the number of members. So 45 members at the start times our multiplier of 1.3 raised to the x. So to answer the second question, we just got to plug in 5 for x. So y is equal to 45 times 1.3 to the fifth power, and we would get 167 members. Wonderful. Part C. This one we are still yet again making an exponential function that represents this. So Barbara made a bad investment. Rather than earning interest, her money is decreasing by 11% every single week. So after 1 week, she's down to $142.40. How much money did she start with? And if she does not withdraw her money, how long will it take before she has less than half of what she originally started with? All right, so let's get to it. So again, we know Y is the amount of money. X is going to be the number of weeks. So I'm going to walk us through the first part. For the second part, after we get our function made, I would recommend that we would just make a table all the way through, and that would help us solve this one. So let's start again, what our multiplier is going to be in this case. So we're decreasing by 11% every single week. So following the same kind of logic from the last couple of problems, we start with that 100%. So that 1.00 over her money. Again, we are decreasing, so we're subtracting 11% every single week. So how we represent 11% as a decimal is 0.11. So we have to subtract 11% from that. So our multiplier is going to be 0.89. 0.89. All right, so moving on, that's our multiplier right here. We got to find our starting value, but we don't have a graph or a y-intercept. They don't tell us the starting amount. We got to figure that out. But we do know right here that after 1 week, she was down to just $143.40. So again, we know that we talked about already that X is the number of weeks, Y is the number or the amount of money that she has. So basically that highlighted section tells us we have an ordered pair of 1 and 142.4. So if we know our equation so far is y equals a times 0.89 to the x, we just got to plug in x and y, and we can solve for our intercept. So we have 142.20, or not 0.20, 142.40 equals a times 0.89 to the first power. So anything raised to the first power is always just itself. So if we divide both sides by 0.89, we find our starting value where a is equal to 160. So that's how much money she started with in that investment. So our equation for this one is going to be y equals 160 times 0.89, all raised to the x power. And again, if you want to solve for the second part, what I would highly recommend doing, make a t-chart, x and y, plot some values, and figure out how much it's going to take, or how many weeks it will take her to get less than half of what she originally invested. Again, we want that money to be less than $80 for this part. So make a t-chart. That would probably help us out for this. And then last but not least, we've got 71D. Larry loves his music. He bought $285 worth of MP3 files on his credit card, but he cannot afford to pay off his debt. Little life lesson, that's probably not a good idea to buy things you can't pay for. If the credit card company charges him 18% annual interest compounded monthly, how does Larry's debt grows as time passes? So how much would he owe at the end of the year if he had no payments for 12 months? All right, let's see here. So first thing we got to do, we are given an annual interest rate of 18%, but we're only applying that monthly. So we're applying that in incremental chunks, even amounts over the year. So we have to take that 18%, divided by 12 to get our monthly interest rate, because it's compounded monthly. We're not compounding it by 18% every month. That would just be mean. So what that tells us is that our new interest rate is actually 1.5%, and that is per month. because it's an annual interest rate. We're not applying that 18% every single month. We're only applying that in 1.5% increments every single month. So that means that our multiplier, if we add that 1.5% onto our 100% of our initial credit card value, which is $285, that multiplier would be, for our exponential equation, 1.015. So now we just got to write an equation. So we have y equals 285, which is the starting amount for the money that Larry spent on his music, times our multiplier we just found, 1.015, all raised to the x, and how many, or how we want to find, again, figure out how much money he owes at the end of a year, where x is now the number of months. So we got to plug in 12 for x. So for this one, y equals 285 times 1.015 to the 12th power. So y is equal to $340.75. There we go. Awesome. So the one that I kind of glossed over, and the one I told I would come back to, is 67. So for this one, all you had to do, there's a ton of different answers we could potentially get for this one. But all you had to do is basically come up with a situation, come up with a problem that could be represented by either the graph, the equation, or the table right here. So there's a whole bunch of different answers. If you come up with anything good, let us know, because we're always looking for new ideas for test questions or homework questions, but that is essentially what we're looking for here. So find a way to write a problem that would match the graph, the equation, or the table. And again, there's a ton of different ways you can do that. So last thing I'll leave everybody with today is that the homework for tonight is 7.1.6. You can skip 73 part C and 78. So only do those selected problems, so you can skip those two. Otherwise, have a great rest of your day, folks. We'll see you all in live class once again on Thursday.